We continue on with our learning target 13C/13D, graphing sine and cosine. So together in class earlier, we graphed a basic cycle for both sine and cosine, and we talked about how it does continue, since it is periodic, that it continues to repeat forever and ever in both directions, and we connected that back to our unit circle concept that we have. In this video, what we're going to focus on is how do I actually graph it if I don't just have a standard graph? What happens if I add a stretch or a compress factor to this, a vertical stretch or a compress? And likewise, we're actually going to look at for the first time what happens if I horizontally stretch or compress this graph. What we are not going to focus on at all is what happens if we vertically or horizontally shift it. So we are going to keep everything kind of starting at around the origin, but we will be stretching it both vertically and horizontally as well now. So a couple things to keep in mind. What that means then is that all of our functions that we're going to be looking at are of these two forms, depending on if we have sine or cosine. So we'll look at graphs that look like y equals a times sine of bx, or y equals a times cosine of bx, where a we don't want to be 0, otherwise if I have 0 times a trig function, I just get 0, and that wouldn't be our sine or cosine graph any longer. We also are going to keep b positive, and x will be in radians. So everything that we're labeling along the x-axis here is going to actually be in radians. We're not going to do any in degrees. A and B are just going to be numbers that we're going to end up scaling this by. We're used to this A value from the whole rest of the school year, that this is our vertical stretch or compress factor. Another thing to keep in mind is we could have a reflection here. If A is negative, then that will actually be a reflection over the x-axis. So let's point out a few key features. So the absolute value of A is going to be the amplitude of our graph, which is how high it is stretching, or maybe how not high it is stretching if we're compressing it. 2 pi over b, so b is this number that's being multiplied to x here. So 2 pi divided by that number is actually going to be the period of this function. So this is what I mean by this horizontal stretch or compress factor. So before, when we looked at a basic graph of sine, if I were to graph it here, remember we had 0, 0, it went up at pi over 2, back down at pi, down again to -1 at 3 pi over 2, and back at 0. So if I sketch this, it's curving through there, like that. Now the period here was 2 pi because this was a standard graph. Now this b value, what it's going to do is it's going to either compress this graph in and kind of make it shorter, and it's going to repeat a lot quicker, or it could elongate it out, and it would be horizontally stretching this so that it would take longer than 2 pi for this graph to be able to complete one complete cycle. B there, although to get the period, this is more useful to have 2 pi over b, but b itself is actually the number of cycles that occur between 0 and 2 pi. So if we end up condensing this down, I could get multiple cycles that happen between 0 and 2 pi, which means that maybe I have 2, 3, or 4 happening. Or if between 0 and 2 pi I don't even have a full cycle, if I've elongated this out, then that means that I only maybe have half a cycle happening between 0 and 2 pi. For all of our examples, our goal will be able to graph one complete cycle. So a lot of our graphs are not going to end at 2 pi anymore. They might end sooner if I'm compressing it, or they might end later if I'm actually stretching it out. Then the last thing to keep in mind, as we've done with any graph this year, if A is negative, then there's also that reflection over the x-axis. We have our kind of standard graph here for sine, but let's have our graph for cosine as reference. So remember, cosine starts up at 1, and from there it drops down at pi over 2, all the way down to -1, back up slowly. This was kind of our roller coaster graph that we're taking, so we can think about this. If I'm in an amusement park, the roller coaster goes down and comes all the way back up, versus the sine graph was this nice wave feature. Now we talked about in class how these are phase shifts of one another, since sine and cosine, depending on where you're at on the unit circle, have places where they kind of repeat when you shift it. But if I'm just looking at one standard graph here, sine is our wave, and cosine is what I'm going to call our roller coaster that we have. So things to keep in mind is you are going to have to know the basic shapes of each of these graphs. So each time I'm not going to go through and plot points in here, because if I have the basic idea of what the shape looks like, there's no need for me to do that extra work. So remember that sine is our wave that we have up here, and cosine is our roller coaster that starts and ends at the amplitude. Now, of course, if there's a reflection here, it's going to start down at -1 and end down at -1, for instance. But in general, if there's no reflection, it's starting and ending at our amplitude. The other thing we're going to have to figure out here, in addition to this, of course, we'll need to calculate what our amplitude is, and we're going to have to figure out what our period length is. But this other thing that we're going to have to figure out is how far am I spacing these? So when I have my period, I know where the graph is starting, and I know where the graph is ending, but how would I get these values in between? Well, those are coming by cutting this up into 4 equal subintervals. So between 0 and 2 pi, I have these 3 other points in between, which means I've got 1 subinterval here, another one here, 3, and then 4. So this length of this interval, although not a mathematically maybe defined term, but I'm going to call it this length of this interval right here, will be found by taking the period, which we'll find up here to start with, and then dividing that by 4. So in this example, for instance, our period here was 2 pi, so our length of our interval is going to be equal to that 2 pi over 4, which is pi over 2 when I reduce it down, which makes sense then that my first kind of tick mark on my graph here as we go along is going to be pi over 2 because that will be our length of our interval. From there, to get the next ones, I'm adding that amount each time. So to get from pi over 2 to the next one, I would add pi over 2, but pi over 2 plus itself, which would just give me 2 pi over 2, which I can reduce down to pi. From there, I'll add another one, so I'm at 3 pi over 2, and when I add my last one, I end up back at 4 pi over 2, which would be our 2 pi value. Now we're going to see us do this in each one of our examples, but I wanted to relate it back to you to how both of our original kind of parent function graphs were created. So let's look at our first example. So for each one of these, it says graph 1 complete cycle. So what that means then is for a sine graph, I have to make sure I have the entire wave graphed. And for a cosine graph, I have to make sure I have the entire roller coaster of this graph on there. We're also going to list the amplitude and the period. So I'm going to actually start out the problem by figuring out, well, what is that a and b value that we had in the original? So kind of off to the side, since it's not an answer that I necessarily need on my paper, I want to think about this. So a was the number that was in front of the trig function. So in this instance, I don't have anything written, but that doesn't mean it's 0. That's our invisible 1 there, since it'd be 1 times cosine. And then b is the number that's being multiplied to x. So here, our b value is going to be 2 for this example. What that allows me to get, and this would be part of the question, so let me fit it right here, is my amplitude for this guy. Remember, our amplitude is always the absolute value of a, so for this example, the absolute value of 1 would just be 1 for my amplitude then. The next thing I need to find is what is my period for this graph. Remember, our period is going to be 2 pi over that b value. So for this example, what that tells us is I have 2 pi over 2, since that's our b value, which means my period for this example is going to be pi. And I'm going to use both of these pieces of information when I go to graph this example for us. What that ends up telling me then is my highest point on my graph, I'm going to label up here as 1, and my lowest point on this graph is going to be, let's clean that up a little bit, our lowest point down here will be -1. The next thing I know is that my graph is going to go from 0 to pi. The reason I know it's starting at x equals 0 is because we're not horizontally shifting this at all, but it's going to end up where the period stops at pi. We could make pi right here, but I'm going to stretch it all the way out to the end of my graph so that I have space to draw this graph in between. If you start your period like way at the beginning, then you have to fit your entire graph in that little tiny area. So I think the easier way to do it on yourself is to spread this out as much as possible. From here to get the next part, I want to go back and look at what trig function I have. I have cosine in this example, which means my graph should end up looking like this roller coaster that I have here. What's going to change are these values down here. Now, since my period length is pi, the reason I know they're going to change is there's no way that I could keep the first 3 the same here, because I can't go from pi and then back to pi again. That doesn't make any sense. I need to instead adjust those values in between, and that's where this length of interval comes into play. So let's calculate that right now. So our length of our interval in general is going to be our period over 4. So for us, our period was pi, and we're going to divide that by 4. Now there's nothing I can reduce down there, but that means that pi over 4 will be the distance I move between each one of these. On each one of these graphs, although we have 4 intervals, we actually have 5 points. So I'm going to switch colors real quick so that we can see them. But I've got this starting point. There's 1 point, 2 points, 3, 4, 5 points on here, which means I'm going to end up needing 5 points on my graph. Although it's 4 intervals, it's 5 points total. So the first point that I'm always starting at, no matter which graph I'm looking at, is going to be 0. Because although cosine starts up here at the y value being 1, the x value that it starts with, if I were to label this, would be x equals 0. Likewise up here, the first value on the sine graph is also 0 for the x value. From here, to get my next kind of set of points, I need 4 more. I already know what one of those is, and that's actually my last point. So I'm trying to find all the in-between points. I'm going to kind of star them, so I'm missing 1, 2, 3 in-between points. My fourth point is actually going to be pi, because I always stop my graphs at the period length, because we're not trying to go further since we're just drawing one complete cycle. To get in between, this is where the length of the interval comes into play. So each time I move, I'm going to add this pi over 4, or add this length of the interval to get to the next point. So 0 plus pi over 4 would be pi over 4. Now when I add pi over 4 again, I get pi over 4 plus pi over 4, which would give me 2 pi over 4. And if I add it one more time, I end up getting 3 pi over 4. And then just as a check always, I should be adding it one more time. And that makes sense because I'd end up at 4 pi over 4, which is equal to pi if we reduce it down. The other one I can reduce if you guys want to is we can reduce 2 pi over 4 to be pi over 2. This should kind of help be ringing some bells to that clock that we were dealing with when we learned about radians. Now, I'm moving kind of on my pi over 4 clock. I went from 0, pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, or pi. So this is similar to what we've already done before. The difference now is instead of it being one of those clocks, I'm going to use this length of interval depending on each of these examples. Now that we have these points, I can go ahead and label my x-axis. So what that means then is I can label the 3 points in between. So the easiest way to do this for me personally, I think, is I'm first going to half the distance, then I'm going to half this distance, and then half the other side of it. That then gives me 4 equal areas, a lot easier than trying to kind of guess and judge it along the way. So I prefer to do the halfway point, the halfway, and the midpoint here. And now let me label them. So I have pi over 4 first. Well, really first I guess I have 0. And then I have pi over 4. This is our pi over 2, or our 2 pi over 4. You don't need to reduce it if you don't want to. Then I have my 3 pi over 4, and then my pi where we're ending. And those came from us finding these 5 points for our graph. And I guess when I say points, I should say the 5 x values on our graph, since the y values we still need to talk about. From here, I actually have enough to create the full graph. I know that cosine starts up at the amplitude, so that means it's going to start up here at 0, 1. It goes down to pi over 4, 0. It goes then to pi over 2, -1, back up to 3 pi over 4, 0, and lastly finishing off at the amplitude, which would be pi, 1. I like to plot the points first because it gives me a good idea that how I'm sketching it. If I were to kind of eyeball this as I go along, it might be really easy to kind of accidentally miss a point and instead go from like 1 to 0 here and then try to fit it. I have to make sure these 5 points are correct on my graph because they're really giving me the shape of it. So from here, as I sketch it, it's curving down and then back up as it keeps going. And that would be my graph of y equals cosine of 2x right there in green. Couple things I want to point out to you guys in this example just to keep track of as you're going through these. when we're grading these, what we're looking for is I do want to see the shape clearly defined. So I want to make sure the cosine graph is curving out, kind of down and around on the shape. I don't want to make these straight lines connecting it, because that would be creating an absolute value like v there, and an absolute value graph and cosine are very different functions. So I want to make sure I'm curving these graphs. I also want to make sure that my x and my y-axis is completely labeled. So to earn full credit on an exit ticket or a learning check or on your final, you want to make sure that all of these points are clearly labeled on here. So if you like to do this work on the side to find them, you're more than welcome to, but I still need to see them labeled on the graph. On the flip side, if you find this easy to do this arithmetic in your head, then I'm okay with that, but they have to be labeled here on your graph. But do take into account, though, the more work you show, the more partial credit I can give you if a mistake were to get made accidentally in your head as you're doing some arithmetic. And just like we want to label the x-axis, make sure your y-axis is also labeled for us. So let's go down and look at our first example that deals with sine now. So our sine graph is going to start and then kind of curve around like our wave shape. But before I get there, let's figure out kind of what is the amplitude and period so I know what this graph looks like. Before I even get there, I'm first going to have you guys pause the video right now and you guys decide what is your A value and what is your B value for this example that says y equals 3 times sine of x over 2. Okay, let's check your A and your B value. So A is the number that's being multiplied in front of the trig function. So my A here is 3. Now B is the number that's being multiplied to x. Well, x over 2 I can rewrite as 1/2 times x. This makes it a little bit easier to see what that B value is, and so I can tell then that my B value is 1/2 for this guy. From here, using that information, I can tell you that my amplitude is going to be equal to 3, since that would be the absolute value of A. And the other thing I can tell you is that our period for this example is going to be 2 pi over the B value, so 2 pi over 1/2. Now this is a perfectly fine answer, but it's not really helpful in terms of me graphing, so I want to simplify this. So instead of dividing by the fraction, it's the same thing as multiplying by the reciprocal. So I can multiply by 2 over 1, so I end up getting a period that is going to be equal to 4 pi, if I can fit it on the screen there. What that tells me then on my graph is that my highest value is going to be at 3 now, so I've got 1, 2, 3, and then down to 1. Oh, that's not very spaced out equally. 1, 2, negative 3. I also know for me to get a complete wave function here for sine, I have to go all the way to 4 pi, so I'm going to stick my 4 pi value way out here so that I have enough space to create this graph. The next thing I need to figure out is, well, what are all the other x values in between? I know I start all graphs at 0 since we're not shifting it left or right, and I need to know what are the other 3 points in between. So I've put the tick marks on the graph, but I've got to figure out what they are. What can help me do this is this length of interval concept. So remember, our length of our interval is how far we're traveling between each one of these. And the way we get that is by taking our period, which for this example is 4 pi, and dividing by 4, since there will be 1, 2, 3, 4 subintervals on here. Well, 4 pi over 4 reduces down nicely to b pi. So when I go to kind of find these 5 points now, if I write out my 5 stars as I'm thinking through these, I know I'm always starting at 0, and I'm ending at what our period is. So in this case, I'm ending at 4 pi. And to get from one point to the next point, I need to add that length of interval, so I'm going to add pi each time. And I'm going to have you guys pause the video again and decide what these 3 in-between points are going to be. So as we check this, since I'm adding pi each time, 0 plus pi would give me pi for my first point. I'm going to add pi again, so pi plus pi would be 2 pi. And if I add it one more time, I would end up getting 3 pi. And then just to kind of double check, if I add it again, I always want to make sure I end up at my period, which 3 pi plus pi does equal 4 pi, so we did everything correct. that's kind of a really good check for you guys as you go through. Some of you might be thinking, well, that's really silly. It's always going to work out. Well, if we accidentally make an arithmetic error, this is one way that you can check that, because if you take your fourth point here and you add the length of your interval and you don't get the period, then something either up above is incorrect, or maybe your period itself was incorrect. So we have to go back then and check that arithmetic. I'm going to use these points now to plot them on the x-axis. So I have pi, 2 pi, and 3 pi that get to go on the graph. And now we get to actually plot it. Just like we did with cosine, the first thing I'm going to suggest we do is start by plotting where are the 5 points before I kind of play my connect the dots. If I just start kind of graphing it, my graph might not end up looking exactly how it's supposed to. So for sine, I know that it's the wave shape, so I start at the origin, it goes up to the amplitude, back down to the negative, and then back up to the 0 value. So when I now connect these together, I'm going to get this nice, I missed it. I'm going to get this nice wave shape as I keep drawing it as it goes through it. Best that I can get kind of with this tablet I'm using. So it curves up, and then it curves all the way back down from there. Now, of course, as we talked about in class earlier today, this graph does keep going. So this keeps oscillating all the way down in both the positive and the negative direction, just like cosine would as well. So I don't want you guys to ever think that this is the only part of the graph and it stops here. This graph does keep going in both directions forever and ever and ever out to infinity. But for the purpose of our class, if I were to ask you guys to graph the entire thing, you'd still be graphing it all year long and forever and ever, because this isn't ever going to end. Instead, it's enough for us to just show what is one complete cycle so that we understand what the graph looks like and how long it takes to complete that full cycle. So in this case, although this looks pretty identical to that original graph of sine I have, it's extremely different. So that original graph we had for sine did this whole complete cycle between 0 and 2 pi here. This graph only does half of a cycle between 0 and 2 pi. It takes all the way out to 4 pi to get the full complete shape. The other difference is it's been stretched vertically now because the amplitude is up at 1. So this is stretching up to 1 at the high, or up to 3, at the highest point, and down to -3 at the lowest point. It's also been stretched out horizontally since it's taking longer for this graph to do one complete cycle. So this has elongated it along the x-axis then. Versus if we go back to our first example, it's actually condensed it horizontally because I can do one complete cycle between 0 and pi. I don't have to wait all the way to get to 2 pi. I can do the entire graph once and do it a second time even between 0 and 2 pi. So this is first example is stretching or condensing horizontally, versus the second example is stretching or elongating it horizontally along the x-axis. It is also stretching it vertically as well. Let's look at our third example here. So just like we've been starting, I'm going to have you guys first decide what our a and our b values are for the example, which is y equals -4 cosine of x over 3. So I want you guys to pause the video right now and decide what does a equal and what does b equal. So let's check this. Remember, our a is always the number in front of our trig function, so our a value here is going to be -4. We do want to take the negative with it, and we'll discuss what will happen with that. Our b value, remember, is the number that's being multiplied to the x, so in this case, it's 1/3. The reason being is, just like in our prior example, I can take x over 3 and rewrite it as 1/3 times x to kind of easier see what that b value is going to be. The next thing I want you guys to find is, why don't you guys decide on what the amplitude is for this function and what the period is going to be as well, and then we will check it. So go ahead and pause the video and answer those questions. Okay, so let's check our amplitude. So for this one, although my a value is negative, my amplitude is going to be +4 since I'm taking the absolute value of this a number. And the absolute value of -4 will be +4. Our period for this example, remember, is our 2 pi over our b value. So we get 2 pi over 1/3, which in this case ends up giving us 6 pi when I multiply by the reciprocal. So let me draw a line here to kind of separate these two problems, since the prior one kind of dipped down a little bit so we don't get confused. But for this example, when I take 2 pi divided by 1/3, I end up multiplying by the reciprocal, and we end up with 6 pi for our period length for this example. From here, the next thing we have to find is, what is this length of interval going to be? And I want you guys to pause the video and decide what you get for your length of your interval. If we go ahead and check it, remember it's our period, which for this example is 6 pi divided by 4, which I could leave like this, but I do want to reduce it down just to make my life easier later, and I know that 6 over 4 will reduce down to be 3 pi over 2. From here, I need to now start let's plot what we have. So my amplitude is up at 4, so I need 1, 2, 3, 4, and all the way down to 1, 2, 3, -4. The other thing is my whole graph is going to start at 0, but then it's going to end all the way out at 3 pi over 2, which I'm going to keep putting way out here just so that I have enough shape, in between. So from here, so I have all of my space. What we're going to do now is let's come up with those 5 points that we have. So I always know that I'm starting at 0. I've got 3 I need to find in between, and then my last point down here should be 3 pi over 2. Or no, I'm sorry, not 3 pi over 2. It should be our period length, which would be 6 pi. So let's fix that. I want you guys to find all of our in-between points, and I'm realizing I had made the same mistake over here on our graph, and that should say 6 pi, since this would be our period length. That makes a lot more sense there then. So why don't you guys pause the video and decide on what these 3 in-between points are going to be. So let's go ahead and check these. So as we're going, remember we're adding our 3 pi over 2. That's where that's coming into play. So our first point is going to be 3 pi over 2. Our second point, if we add it again, will give me 6 pi over 2, if I try to fit that in there, which we could reduce down to be 3 pi. From here, if I add 3 pi over 2 again, I'm going to go back to the unreduced form so that I have a common denominator, and I end up getting 9 pi over 2, which if I add again, I get 12 pi over 2, which would give me back to 6 pi, so I have done everything correctly as we keep checking. So I didn't write it this time, but remember each time you're adding this 3 pi over 2. So 3 pi over 2 plus it again, 6 pi over 2, 9 pi over 2, back to 12 pi over 2. From here, when we go to graph this, I need to plot these points in between. So to make my life easy, I'm going to find the halfway point, and then the halfway, and the halfway point again, so it gives me a nice equal distance. And if I plot these, I have 3 pi over 2 first, I have 3 pi, I'll take the reduced form instead, and then 9 pi over 2, and then 6 pi. I'm going to have you guys go ahead and pause the video again and graph it. Remember, keep in mind that this is a cosine graph. So if we're going to go ahead and check it, our cosine graph always kind of starts up at our amplitude and dips down. But remember, I have something else happening in this problem that we haven't looked at an example for yet. That negative, although it didn't affect the amplitude, is going to be our reflection. So I'm going to keep that in mind, and it's going to be a reflection over the x-axis. The first thing I'm going to actually plot is what would it look like if there was no reflection. So if there was no reflection on this graph, it would start up here at 4, come down to here, back up, and here. I'm going to do this in dotted lines just so that we can see the difference here, since this graph will have a reflection. But if there wasn't a reflection, our graph would look like that guy. Since there's a reflection, I'm even going to switch colors so we can see the difference here. I'm going to be starting down here at -4. Now when I reflect over 0, 0 still stays. I reflect and I'm up at +4, back down at 0, and then when I reflect this over, I'm ending up at -4. Now when I go to connect this, it's giving me this nice pretty curve, as it goes through there. And that would be our graph when I have cosine, where it's actually been stretched out both vertically and horizontally, and there's a reflection over the x-axis. So there's definitely a lot going on in these examples, which is why right now we are only focusing in on what happens when we stretch or compress, and not worrying about what happens when we horizontally or vertically shift these graphs. Okay, our last example for this guy says y equals -2 times sine of 3x. I'm going to go ahead and have you guys pause the video right now and have you guys do the example, and let's see what you end up getting when we check it. Okay, so let's walk through this together to check our work. So the first thing I'm going to do, I'm going to find my a and our b values. So our a is the -2, since it's the number in front of the trig function. Our b value this time is 3, since that's what I'm multiplying x by. A couple things I'm going to keep in mind is I do have a reflection over the x-axis, since the 2, or the number in front, is a -2. I also know, I'll add it up here, my amplitude is going to be +2, and my period for this example is going to be 2 pi over 3. Since it is always, remember, 2 pi over our b value, which does not reduce down, so I'll just leave that alone. The next piece I'm going to go ahead and find is this length of the interval. And when I do this, I have my period, which will be 2 pi over 3 all over 4. Now this is definitely something I want to reduce down to make my life easier, so I get 2 pi over 3 times. Now remember, 4 would be the same thing as 4 over 1, so when I multiply by the reciprocal, I get 1/4, which means I'll end up getting 2 pi over 12, which I can reduce down even more to be pi over 6. So that means each one of these is going to move pi over 6 units along the x-axis. I'm going to start labeling over here, so I've got up here at 2 and then down here at -2. I know that my period here is 2 pi over 3. I am going to be starting at 0, and I want to find the 3 points in between. So when I do these, I'm starting at 0. I've got 1, 2, 3 more I have to find, and I should end up at my period, which is 2 pi over 3, and let's see if we do. So I'm adding this pi over 6 each time. So when I add pi over 6 to 0, I just get pi over 6. I then get 2 pi over 6, 3 pi over 6, and down here I would end up with 4 pi over 6, which makes sense since 4 over 6 will reduce down to 2 over 3. Also up here on our 2 pi over 6, I'm going to go ahead and reduce it to pi over 3. Again, if you guys don't want to reduce these, you don't have to. 2 pi over 6 is is a perfect example, or a perfect answer to put on your example as well, since they are equivalent. When we go here, I'm going to end up labeling the missing ones that I had. So pi over 6, pi over 3, and let's go ahead and reduce that one too, pi over 2. Why not? If we're going to reduce one, let's reduce them all. So that would be pi over 2. And the last thing I have to do is let's go ahead and plot these. Well, since I have this reflection, I know that I'm going to end up flipping my points, but the first thing I'm going to pay attention to is the fact that this is a sine graph, so that means I'm starting and ending at 0. If this was not a reflection, I'd go up, go back down to 0, back to -2, and back up. So I'll kind of sketch that again using dotted lines through it. So the green graph here would be if there was no reflection, so this would be if it was y equals +2 times sine of 3x. But since our problem had the -2, I'll go ahead and do the reflection here, which takes this pi over 6 value down and flips up the pi over 2. Of course, the ones on the x-axis aren't going to change because they're reflecting over themselves. So this will curve down, and then from here it's going to curve up and over. And that is our last example for this guy. And the end of learning target 13c/13d, since sine and cosine have so much in common, it just kind of makes sense to do them together.